Hello everyone. This video is about binomial array. Binomial array is different from uniform arrays in the sense that if you have a binomial array, their excitation, their excitation coefficients may not be the same. So this one may be I naught, and this one may be D I naught, D I naught, and then this one is I naught. So this is one of the characteristics of binomial array. In a uniform array, right, you have the excitation coefficient the same for all elements. So before going forward, I would like to tell you the background rationale for this array. First of all, if we have a two-element array, we will produce a radiation pattern like this. And there won't be any silo. Uh, by silo, I mean some of the radiation element, some of the ropes here are pointing to the unwanted direction. Right perhaps we are going to receive the signal from the direction of the major rope. But then this one here is pointing to a direction that we don't recognize. So it is only good for hacking. We are trying to avoid any silo. So uh, we know that right, if we have only two elements, we will not end up with any silo. Uh, for two element array, it has the radiation pattern is determined by the array factor, which is sine and then n by 2 divided by sine by 2, 5 divided by 2, uh, where n is equal to 2. So in other words, if we continue to explain this function, what we end up with here is sine 2 by 2, 2 5 divided by 2, and this one here. So eventually we want to with cos and then 5 divided by 2. And now, uh, what if we have another array with the radiation pattern being uh, this one and then self-multiplied by n times. So for instance, if this one is the array for two elements, and right, uh, we have an array such that the array factor is equal to AF2 and then n minus 1, self-multiplied by n minus 1 times. If this one doesn't produce any cycle, then um, the radiation pattern self-multiply with each other by n minus 1 times shouldn't produce any cycle at all. Uh, but on the other hand, right, the gain will be enhanced So for instance, for two element array, we have the pattern like this. And if we increase it, say up to four elements, then we may end up with a pattern like this. But there is no cycle at all. So this is the new one. Uh, and this one is n equals to 4. And this one is n equals to 2. Uh, but there you will not see any cycle here because of the mathematical nature of this array function, the array factor. So now you may wonder, if this one is like this, right? Then what we end up with here is going to be cosine phi of 2 y divided by 2, and then n minus 1. And by the way, we have a 2 here, yeah? We have a 2 here, so there should be 2 here. We have 2 n minus 1, and then cos y over 2 n minus 1. So you may wonder, right, what does it really look like in an actual array? So I'm going to show you. We have a two elements array. Say these two elements. We have an array function being equals to 1 plus and then 3 5. So this is the array function for two elements array. And if the excitation coefficient are the same for this element, then this is the array factor. And this one is also the same as this one here. So if I'm going to expand it, so this one, as we already know, is equals to 2 cos phi divided by 2. And now we are going to end up with an array function with the array factor being self-multiplied by n minus 1 times. So what do we get? So in the right-hand side of this equation, we have 2n minus 1 cosine and then n minus 1 of phi divided by 2. And how about the right side of the equation? The, the left side of the equation is going to be this one, n minus 1. And now what we can do is we actually use binomial theorem to explain this. And if we do that, what we are going to get is n1, the next term is n choose 1, and then the next one is n minus 1 choose 2. And then the exponential term here is going to be j. And if we continue this process, we will have n minus 3, 3, and until at the end, we end up with, um, sorry, still n minus 1, until we end up with n minus 1, c n. And then This one is n minus 1. And minus 1. And then at the end, we have 1 here. So this is what we are going to get for the left-hand side of this equation, the equation 1. And the right-hand side is equal to 2n minus 1 cosine n minus 1. So essentially, it is actually an array similar to the uniform array, with an exception that the excitation coefficients are different. They are not going to be uniform anymore. Right? So this one is 1, and this one may be n, and this one may be with a higher value. So now let's take a look at an example. Suppose now, suppose n is equal to say 3. And if we do that, then the left side of the equation here will be AF equal to 1, 3, and then 3 minus 1, which is equal to 2. So here, what we are going to get is 2. Is it going to be good enough? Let me see. Maybe 4 is better. 4. Let's see, 4. And the left side and the right side of the equation is going to be 2 and then 4 minus 1, which is 3. 3 minus 1. So this is what we are going to get. And we will explain it. This one, we will explain it. Let's say 1, 1, 1, 2, 1, 1, 3, 3, 1, 4. So 1, 3, 3, 1. So what we are going to get is the left side of the equation is going to be 1 plus b j, and then b j 2, 5, and finally we will have an answer, and then j 1, 2, 3, 4. So 3. And according to our derivations, we know that the final um, array factor should be equal to this one. So this one was 2 times 2 times 2, which is 3, which is a, right? So this is one is going to be a, and then cos, and then sorry, this one should be 4. Uh, this one. So this one is B. B. So we have 3 here, and then so this is what we are going to get. And in the actual implementations, you just need to have 4 array of the same identical element, but they are excited with different excitation coefficients. This one, 1, and this one, 3, and this one, 3, and this one, 1. And now, the eventual radiation patterns will be somewhat like this. there won't be any side loop. So this is the beauty of binomial array. So uh, to sum up at this stage here, the advantage of binomial array is low side loop. So what about the disadvantage? The disadvantage is low gain. The gain is very low. And no matter how many elements you have added, you can hardly go beyond uh, n. For example, when you have an n element, the n is equal to 100, so the gain of your antenna is not going to be more than 100. It may be just somewhat like 10. So now, what we are going to do is to explore the directivity and the intensity of this binomial array. Now we have the array here, right? Suppose we are going to have an n element. We don't know what n it is. So n element. And the left side of the equation is going to be this guy and self multiplied by n minus 1. And the right side of the equation is 2 to the power of n minus 1 and cosine of 5 divided by 2 to the power of n minus 1. So this is the array vector that we are going to end up with. And if we expand the left side, this is what we the kind of equation that we are going to get. And how about the right side? The right side uh, of the equation is 2 to the power n minus 1 and then cosine n minus 1 of 5 divided by 2. And what we can do is we make use of this function and derive the intensity and directivity and also the half power beamwidth. So the first element of this chapter is intensity. Intensity, by definition, is power per unit solid angle. And now we are going to explore what they are. And we know that U is equal to S R squared, where S is the power density, the alpha is power density. And R is the distance between the array and the destination, or say, and the receiving end. And now we are going to find out what what they are. And S, first of all, S. S, by definition, is going to be the magnitude of the electric field divided by 2 eta. Uh, the eta uh, is the characteristic impedance. So now, how about the magnitude of the electric field? Uh, it's very simple. Right? It is the square of this term. So it's going to be uh, 2, maybe I should write down A, F, and then 2 eta. And you can just continue from here. S, uh, U is equal to this one. Right? U is S R squared, so it will be um, A F 2 eta R squared. And now our job is to find an equation here. Yeah? So this is going to be 2n minus 1, and then this one here, and then 2, and then 5, 2. And do not forget that 2 eta. So this is going to be the intensity of this array. Now we know the intensity. Uh, the intensity will be expressed as phi times what is phi? Phi here is kd cos theta. So this is the count of uh, wave number times the circulation between two labeling elements times cosine of the theta. Theta is an observation angle. Uh, so now we continue. We continue from here. And what we are going to do is to re-express this intensity. We have already known the intensity is given by as a power per unit solid angle. And the expression for the intensity is like that. And what we are going to do is we are going to simplify this expression. So now, take a look in this expression. U is equal to this amount and cosine of this function. And we know that the maximum value of cosine uh, of whatever degree uh, is 1, just like any other trigonometry function. The maximum value is 1. So we know, based on the information here, U max is equal to this amount. So 2 n minus 1 divided by 2 eta. So we are going to continue from here. So U is equal to 2 and we also know that U max is going to be 2 So based on these two equations, we know u can be rewritten as u max, and then the cosine function. So u here is the intensity, yeah. I can just say I'm not going to write too much text down. Now the next thing that we are going to do is to use this piece of information to derive uh, the average intensity. So what we are going to find out is U average. And what is U average? The average of the intensity. So it is by definition, right? The intensity is the power per unit solar angle. And what we are going to do is, right, we use different formula. And this formula is 1 over 4 pi, and then to the total power radiated. So the total power radiated divided by 4 pi will be a average value. And this average value is applicable to all directions. It's basically, eventually, it will be a constant. And now, if we further explain it, this one will be u, and then pi, 2 pi, and sine theta, d theta, and then d phi. And what we are going to do is we simplify this expression. We know theta and phi here has no relations with each other. So we can do this. And u, right? We are going to substitute u and cosine 2 n minus 1 of this one here. And then sine theta d theta. What else, right? Before going forward, we are going to explore an alternative to solve this integral. Right now, we know that this one is definitely resolvable. This one will end me up with 2 pi. And now we don't know what this one is. So what we are going to do is we find out the what is this one? This one is by definition kd cosine beta, and this means d theta is going to be kd and then sine theta. And with some arrangement, we know this one was sine theta d theta is going to be d phi and then kd. And also when theta is 0, when theta is 0, and this limit is going to be cosine of 0 degree. And this one is going to be kd. And when theta is pi, And let's see what we are going to get. Minus KD. So essentially, we have got all the information where we can resolve this. We can rewrite this equation. Right now, we are dealing with U average. And this U average will be used to determine the derivative. Now let's move on. U average is equals to this one here, yeah? 2 pi, 4 pi, and we end up with 2. So U max divided by 2. And here is going to be an integral with minus KD. Sorry, it should be KD and then minus KD. And this one here, cosine 2 and minus 1. And then, and according to here, this sine theta times d theta is equals to d and then minus kd. So we are going to do some rearrangement on the fly. So this one kd can be moved to outside of the integral function. And we have minus here, and we can just simply change the order of limits. Kd and then minus kd. So now the equations here become much more handleable. And we move this 2 into here. Then essentially we are going to have a function kd and then kd divided by 2 minus kd divided by 2. And then x and dx. And you can use the integration table to resolve this one. Or equally, if you don't want, you can also find other means to resolve it. But no matter what, at this stage here, we immediately know the directivity. The directivity is going to be, by the definition of IEEE, is going to be U divided by U average. And what is U? U is U max times cos, and then pi over 2. This is the original function of U, and divided by this terms of expression. And I'm going to rewrite this in here. We allow running out of space here. So D, the directivity is U and then divided by U average. And according to here is U max and then cosine 2 n minus 1 and then pi over 2, which means cosine theta divided by 2. And at the bottom, we are going to move this function into here. So it will be this one here, U max divided by KD minus so this is the formula for the directivity. It doesn't matter what kind of separation between two labeling elements you have, and you can just use this one here to calculate the directivity. And now we have U max on the top and bottom. You can cancel it off. So eventually the formula will be like this. Now, what happened? What if the separation D, which is the separation between two labeling elements, what if D is equal to lambda divided by 2? So in this case, KD is going to be 2 pi over lambda, and this is going to be pi. And if this is the case, then the directivity, which is the function of beta, uh, is going to be pi. And then, um, sorry, 2, and then the big bracket of function, right? This one is pi cosine theta divided by 2. And at the bottom, we have a function here, yeah, pi over 2 and minus pi over 2. And we have the function here, x dx. So for all the array with the value of d being equals to lambda divided by 2, you can use this function. And if d is not in this value, d is um, uh, different value, then we can use this formula to work this out. Now, let's take a look at an example. Suppose n is equal to 4. Now, suppose we have a binomial array with, say, 4 elements, and d is equal to lambda divided by 2. And now my question is, right, what is the directivity? What is the directivity? So based on the expression here, we can work this out. D of beta is equal to pi cosine 2n minus 1, and then pi and finally, right, we just substitute the value here. Now we know we want 4 elements, so 4 minus 1 is d, so this one is going to be 6. And how about here? You can just do this, separate. and then cosine 6. So this is what we are going to get. And fortunately, it's not difficult to resolve this function. On the internet, there are plenty of resources where you can learn how to resolve this bottom expression. And if not, well, we can just use another technique. Either way, uh, the maximum value here, right, we can find out d max. D max is going to be uh, the maximum value of cosine of this function to the power 6 is going to be 1. Yeah, the maximum value has to be 1. So d max here is equal to pi over 2 cos dx. And according um, to some internet resources, we know this value is going to be. Um, yeah, we need to find out. Just a moment. And I'm going to show you the how we can use MATLAB to solve it. So now I'm now using the MATLAB window I'm now using the GNU object to solve this function. So integral of cosine of x to the power 6, and then we integrate x, and then you will be from pi divided by 2 to pi divided by 2, minus pi divided by 2 to pi divided by 2. And now we are going to solve this. So it is equal to 5 pi divided by 16. Pi divided by 16. So 16, the answer is 3.2. And do we actually need to use this way to find out the maximum directivity? The answer is no. Right? What we can do is we can use the basic formula to find out the exact excitation coefficient of each element. Say in this case, we have 4 elements, and now we use the Pascal triangle to find out 4 elements. One, this is for 2 elements, and this one is for 3 elements. And 4 elements, 1, 3, 3, 1. And based on the coefficient here, we know the maximum directivity is going to be 1 plus b plus 1 square, 1 b1, huh? And then 1 plus b square plus b square plus 1 square. And the answer here is exactly 3.2. It's completely consistent. So we don't really need to use the resolve this function in order to get the value of Emax. But on the other hand, if d is not equal to lambda divided by 2, then you cannot use this way. Uh, so now we have some knowledge of directivity of this binomial array. What else do we need to know? Perhaps we also need to know the half power bandwidth or even the first new beamer, half power beamer. So why don't we just use this function to find it? And based on the information here, we know the directivity is d max, and then times this value. And if d is equal, this one right is equals to d max times 0.5, then we are going to get the half power so-called. So this one is going to be equal to pi 1 over 2. And eventually, right, we need to find out the angle. We solve this equation. We don't really need a calculator to. We don't really need a MATLAB to do it. We can just do it by hand. So this guy here is cos pi a beta divided by 2. And obviously, this one here is a cos. And of course, you just do this. And we end up with cos theta. And of course, at the end, you just need to a cos, and then 2 pi, and then a cos. And based on my calculation here, beta should be equal to some value. And you have to check the value to make sure the value is within the visibility range. Let's check it. Uh, so, EQN, and then X. It takes time. But anyway, this is the one of the way to solve it. According to my calculation here, um, Peter eventually will be either 5.017 or 1.265. Uh, the half power beam, this one is larger than pi. So the only value that is left is this one here. And imagine we have an array like this. And the half power beamwidth is going to be somewhere in here. So if we have an angle here, 1.659, and this value is going to be the same. And the value here is going to be the half power beamwidth. And based on the information here, the half power beamwidth is going to be uh, pi minus 1.269 times 2. So times 2, so what I get is 34.9 degree. And how about the first node bandwidth? We can use the same function to find out the first node bandwidth as well. What we can do is uh, the we use the directivity function or even the intensity function. So the intensity is U max, and then cosine 2n minus 1, and then uh, divided by 2. And um, to find all the nodes, we are going to uh, we need to set this function has to be equal to 0. Should be equal to either 0 or pi. No. Pi divided by 2. Pi divided by 2. Remember, it can be plus or minus. And the next one is going to be b pi divided by 2. And the next one, 5 pi divided by 2. So we have to explore all the possibilities. So we start from here, pi, case 1, let's say This one is pi divided by 2, and beta is 1. The only value that you end up with. This one is 0. Or equal or beta is pi. Now case 2. Case 2, we have this one being equal to minus pi over 2. And with this in mind, right, we have minus 1, and then this one is going to be pi. Actually, pi doesn't work for here. 0. This one is pi. So we end case 2 now. And how about 3 pi over 2? So case 4. 3 pi over 2. And based on the information here, there is no solution. And if we continue this process, we will end up with the same conclusion, no solution. So we have only 2 nodes here. So this means if you have a binomial array along the z-axis, then according to what we have got here, the half power beamwidth is somewhat in here, 34 degrees. And the nodes according to here is 0. So this means here we have 0 and pi. Other than that, there will not be any more 0, any more nodes. So the first node bandwidth is going to be pi minus 0, which is 180 degrees. So if you have any question to the comments box, and I will try to answer your question. I apologize to all the students. I made the mistake in the last video. That's why I had to delete it. And now this one hopefully is the final version. Thank you very much.